So, this lecture is the continuation of our previous lecture, that is lecture number 2 of the module 7. In this lecture, that is lecture number 3, I will be continuing over the previous lecture, and in that we discussed the voltage source converter based HVDC transmission system, and also the basically the nickname given by ABB is HVDC Lite and by Siemens is HVDC plus. But here the major difference between the conventional HVDC transmission and this the VSC based HVDC transmission system, here we are using the voltage source converters, and in the conventional we use the current source converters. So, the diagram for the voltage source converter based HVDC system, here you can find that the AC system is having this converter transformer, then we are having some filters to filter out the harmonics, then we are having the reactors, and then these are the converters, and these converters are basically based on the IGBT technology, and we are using here the shunt capacitors. So, that is the DC capacitors for charging and discharging during the to maintain the voltage across this. However, in the CSC it was a smoothing reactors was in series with the line was used, and that is why the current control we were making the voltage here the current the constant in the DC link. So, I will go for the some control philosophy. Already we saw the control philosophy for this conventional HVDC system. Here for the HVDC Lite, again repeatedly I am saying the HVDC Lite means the voltage source converter based HVDC transmission system, and its control again there may be the two converters, one will be your sending end and other will be your receiving end. So, the rectifier of HVDC Lite applies basically uses the active and reactive power control, while the inverter basically uses the DC as well as the AC voltage control, AC of the AC side of the inverter and the DC is the DC link voltage. So, in any system you are having one sending system, one is your receiving system. I am not talking here the your rectifier and the inverter, because there is a possibility this HVDC Lite can be used for the passive load, then it is a sending and the receiving end. The receiving may be your load and sending may be your rectifier. So, similarly we can, if you are having the power you are having two converter, one is a rectifier, another your inverter. So, you can say the sending end is a rectifier and the receiving end is an inverter. So, in this sense we can say the active power, that is the real power, is controlled by the phase angle of the converter's output voltage, and the reactive power is basically controlled by the magnitude of the voltage. We know very well, because the active is the sending end the voltage, this is the delta which is the phase angle, basically it is the real power control. However, the reactive power is controlled by the voltage magnitude. So, this very well we know the QB relation and the P delta relation very well, and the same applies here as well. Although no doubt if you are changing the delta, the reactive power also changes, but this change is a very insignificant. That is why we say that the real power is directly controlled by the delta, as well as the reactive power is directly related to the voltage, as well as if you are changing even the converter voltage, the active power also going to be changed, and but that change is not very significant. So, and another big advantage of your HVDC Lite control system is that we can have a both active, that is the real power, and the reactive power that can be controlled independently. So, we can control these two independently, and that is the beauty of IGBT based voltage source converter HVDC transmission system. In the receiving side, you will see the DC voltage. In the receiving side we are having the DC link voltage. You can see here this is your the DC here the DC voltage, and the inverter is another side receiving and at that side. So, this voltage basically the DC voltage is controlled by the phase angle of the converter output voltage, where the AC voltage is controlled by the magnitude of the voltage the converter voltage. So, these are as I said here in the beginning, that is the receiving end or your inverter basically utilizes and it controls the DC as well as the AC voltage. So, in the more detail we can see the rectifier controller, what it does. Basically the rectifier controller consists of 4 parts. One will be your power flow control loop, means the power flow here we are talking about the real power here I want to say the real power flow control loop, that is a P control loop, and another we are having the Q power, that is a reactive power control loop. Then we are having the phase lock loop, that is called PLL, that is used to basically generate the firing pulse etc., that is required, and then we are having the pulse with modulated firing pulse firing schemes. So, all these 4 loops are there, and they are having the control block individually, and that will be used for the simulation and other purposes. For active power here for active power control, the DC power basically that is a PDC can be calculated by the multiplying the direct current and the direct voltage. It is very well known in either the conventional HVDC system or your the HVDC Lite or VSC based your HVDC transmission system. The DC power, it is nothing but your this P is equal to your VDC multiplied by the IDC. So, the reactive power controller is normally a PI controller, the proportional integral controller. The PI controllers are normally used for the reactive power control. The measured Q reactive power and the desired reactive power are the input to the controller. Means in other sense, you can see for all these 2 points, I can say our this PDC, this DC power, it is nothing but your VDC multiplied by your IDC. So, whenever you want to control the power, you can control one of these quantity or both of them, then you can control the PDC. Here I am talking for the controlling the reactive power. Here this is a control block. Here you are the Q ref, what is your reference reactive power you need, and what is your measured value. This is a plus and minus. Here I can say Q measured value, then this is given to your controller. So, this is basically control block where we are trying to set. Means our intention is to try that this error should be minimized by this controller. So, we want that if this value will be 0, the error difference here, this will be equal to this, which is our intention. So, whatever the Q you want, you can fix and you can make your controller so that it can be equal to the Q reference, and that is basically input the difference here going to the controller. So, the outputs of active and reactive power control loops are the input to the pulse width modulated pulse generator. The output of this along with similarly we can go for the real and reactive power. This is a reactive power, similarly we can go for the real power, and these two inputs are given to the pulse width modulated pulse generator, and then it is generating your firing angle and then your converter as well as the inverters. Here because we are controlling the real power and reactive power. So, this input is given to your this pulse width modulated control of your rectifier. The PLL provides basically synchronous signals of a pulse generator. Here phase lock loop provides the synchronous signal of a pulse generator. Pulse with the modulated pulse generator sends the pulse signal to the drive the valves, or you can say IGBTs in the converters, and thereby we can control the quantities accordingly. By the rectifier controller, the rectifier can produce active and reactive power as a designations. Means whatever you want, as I said here, you can have, even though similarly you can have your this controller. This is your P ref, means how much reference setting you are doing, what is the P, which is actually this is a measured value, and then it is given to your controller. So, this output of this controller is as well as the output of this controller is going for the rectifier pulse with modulated scheme pulse generation, etc. Similarly, if you are going for your inverter control, so in inverter side the pulse with modulated pulse generator and the PLL in the inverter controller are the same as the rectifier, because the pulse generation scheme as well as the PLL, because this is used for the synchronous pulse generation, both are the same, similar whatever you are using in the rectifier circuit. Besides, we require the two control loops here. There are one is your AC voltage control loop and other is your DC voltage control loop, whereas there it is a real and reactive power control loop. So, in whole HVDC light scheme there is a 4 control loops, 2 loops for your rectifier and the 2 loops for your inverter, and the inverter here it is we are controlling the AC voltage as well as the DC, and that is why this is called the AC voltage control loop and the DC control voltage loop. The PI controllers are used here for both AC as well as the DC control loops. Here we are using the proportional integral controller. However, some people are doing some research and some more advances are using some even the artificial intelligence based controllers along with the PI, and when also people go for the other double derivatives here and their controller people are trying to give the better and better performance. The inverter controller can control the AC and DC voltage of the receiver system, because it is receiving center in the HVDC light, and these controllers are used. Now, one of the major advantages of having HVDC light in terms of cable, because it gives a lot of better features compared to the other cables, that is the AC cables, and those differences that you can say that what are features are having the HVDC light cables. You can see first one, it is your underground and underwater, there is no visual impact, means the HVDC light cables are buried underground or underwater. So, there is no visual impact from the power cables, so no visual impact at all. HVDC light cables are made using a strong polymeric insulation material, contains no oil. However, if you are going for the larger cables, you can put some oil inside, and that is one of the big concern, but here it is not required. You can use a strong polymeric insulation material and that will solve the purpose. Another is said that there is no electromagnetic field I mean to say that the HVDC light cable do not have the same health concern as the AC power lines, because they emit no varying electromagnetic fields. No doubt you know the DC it also emit the field, because once current is going, you know the flux is around this. So, the magnetic fields are there, but it is not varying. However, in AC it is alternating. So, the effect of this varying electromagnetic fields are more dangerous compared to the steady state. And also the cables and the converter stations are shielded normally, and there was which results no electric field. So, electric field is almost 0 because it is shielded and it is grounded. So, it is not coming out, but this your electromagnetic fields come out even the DC case also, and this basically this is not varying. So, it has a less hazardous than compared to your the time varying. So, it is not a same health concern. Another advantage of the DC cable, this is HVDC light DC cable we are talking, because it has a low magnetic field. And how come? Means the magnetic field are eliminated by having the HVDC light cables laid with the anti-parallel DC currents. What we do normally, your going and incoming both are if in one here itself, then what will be at the resulting magnetic field will be decreased, and it is with the distance from the cable. Means I want to tell you here that if you are one cable here is going, that I can say the current is going inside, and if you are having one conductor it is coming out and this is in one. So, what will the field of this, and this will be going to nullified, and finally, if we will say the wider range the electromagnetic field is going to be minimized. So, it is a low magnetic field. So, it is possible to have one conductor that is a go, one is come. So, this can interpret this field is going to be cancelled by this field, and that we have the minimum impact. No doubt I cannot say that is 100% eliminated, that is why it is said here it has a low magnetic field. Another concern, the feature that is advantage of HVDC light cable is that it do not make noise as the do AC transmission lines are doing. If you are having a transmission line, so it is a lot of humming noise as well as the corona noise, you will find hissing noise etc., that is not there in the cables. Noise within the converter building, although the properly designed acoustic property of walls and roof, normally we noise are basically reduced if, because the converter stations are inside the building. So, if you can have some acoustic another property of the roof etc., so that noise cannot come outside, and then we can eliminate or we can reduce that one. The converter design can be designed in such a way to minimize the noise and to meet the local noise requirement that can be done. So, that we can also reduce the noise generated by converter station itself, and also by designing the roof and walls we can also reduce that noise level. So, it has a low acoustic noise compared to others. Another it is said that it has a low overall environmental impact. I mean to say that the buried cables there is no electromagnetic fields, the freedom from the oil leakage, there is no oil field. So, there is no oil leakage, it has a low impact on the converter station structure, and also the no electromagnetic fields. I mean to say that if it is buried inside, and also if you are having the anti-parallel, so minimum and also buried, so impact of this electromagnetic radiation is going to be very less. The cables are operated in the bipolar mode, as I said. In the bipolar means one is go, another is a come conductor. So, one cable with the positive polarity, another with the negative polarity is basically, then it is happening this whole is a magnetic field is going to be minimized. Now, here we can see that now we are comparing that the AC underground cable with your DC light cables or HVDC light cables. So, you can see the DC cables require only the two cables between each converter station. Here one is the positive, another negative if it is in bipolar operation. If it is a monopolar operation, one is the your go, another is the return conductor, like that. So, we require only two cables even though we are going for the bipolar operation. Unlike the AC cable, you know here in the AC cable we require three conductors. If these three conductors may be in one cable, the three core, we can say three core cables, or we can have the separate single core cables, then we require three. Here we require only two cables, and normally these two cables may be put in one, and there is a two core cables can be used. Unlike AC cables, which generally have a technical limits of around 100 kilometers due to the reactive power charging and the losses, that we cannot exceed this, even though earlier it was not more than 50 kilometers. So, now it means with the help of various insulating materials and advances in those technologies, people claim that even though they can construct the cable AC cables of approximately 100 kilometers. And we cannot go beyond this, because if you are going beyond this, then what will happen, even though your receiving end, that you are not taking a single ampere of current or a power, your the sending end current is the full load rating of this cable, and thereby if you are exceeding the receiving end power, this cable will puncture and burst, and also there is a huge losses. So, the DC cables are having no such limits, we can go up to the thermal limit. So, that is why the DC cables are more preferred, especially if you are having submarine, or you are having the cables in the sea, or you are going for the longer distance. DC cable can carry up to the 50% more power than the equivalent AC cable, means it can go up to 50% more, because as due to the charging effect. So, it can load more, and that is why it is more stable as well. So, there is no need to install the groups of the cable to achieve the required rating, that is very clear, that is you cannot. So, there is no need of go for several cables, so that you can achieve this same rating. So, that it is already the 50% higher than your AC cables. So, the DC cables have a longer life expectancy than the AC cable due to the lower operating stress level of around 20 kilovolt per mm. Here, if you are having a cable rated for, let us suppose 500 kilovolt, means it is a stress level is only that voltage. If you are using the 500 kV AC, it means that the stress level is going to be multiplied by under 2, because we have to see some stress at the peak value. So, that is a more stress, and that is under 2 times for the same voltage rating. So, the life expectancy is more, because the stress is less, and once the stress is less, then we can certainly say that your cable will have a more life compared to the AC life. So, the DC cables are known to be longer life compared to the AC cables for the same voltage rating, because it has a DC cable has a lower operational stress compared to the AC one. If we will talk about the reliability, because that is also one of the big concern, the major concern that we can say based on your cost, your operation, your its life, its reliability, all the things are coming into the picture, and then that is now I am talking about the reliability. The reliability basically can be based and can be categorized in the two terms. One is the availability, another is the maintainability. In availability, to ensure the high reliability and the availability, the HVDC design principle includes, normally we design in such a way that we can achieve the more reliable operation of HVDC system or HVDC light system. So, it is a simple station design, that the station should be very simple, it should not be very complex. If complex is there, so there is always possibility of the problems in the various elements of the system, and then the reliability goes down. So, we want to design our converter stations so simple that they should have the fewer elements, and also they should have more reliable. So, the use of the components with the proven high reliability, as I said, if you are using the elements, you should use the few elements as minimum as possible, so that the design can be simple, and whatever the elements you are using, they should have a high reliability standards, high reliability contents, and then we can say that overall the system will be more and more reliable. So, another is also, because it is not also possible that manually every time you are inspecting. So, we should have some mechanisms to have the automatic supervision, and so that you can, if there is some problem here and there, then by automatically it should be corrected, or you can know by sitting in the somewhere station or somewhere far end, you can see whole system whether the problem. Another is to use the redundant or to the backup control system and the equipment such as the measurement pumps, etc. Because as I said, there is a lot of heating problem is there, because a lot of heats are generated due to the switching here and there in the converter. They are not a perfect switch, they are having some resistances. So, there will be some active and reactive power losses in that, and thereby we require some heating, and for the cooling it we require some pumps, and then if suppose one pump you are using and this fails, then whole converter station must be stopped. So, what we do, we go for some reliable operation, means we have some redundancy. If one pump goes off, we can go for another pump, and then we can start the operational problem without any delay, or we can just even though continue with you help of another pump. And what happens then the later on we can repair one and then again put into the service. So, that we have to go for the redundancy of the elements. sometimes a measuring device, if one measuring device is fails, so you do not know what will be the temperature for measuring the measuring device like a temperature. If the temperature meter fails and it is showing very high temperature, what will happen? Then you have to stop your session. So, we should have a second one, so that we can verify it. So, redundancy and the sometimes the backup control, because if one control fails, then also we need some secondary and backup control that will take care for the running operation of the system, and later on that can be replaced and that can be corrected. So, these are the basically the design principle. It is not only for HVDC light, but also it is true for the conventional HVDC station. So, whenever you are having these criteria in your mind, then I can say the availability of that station will be much more, and it will be more reliable. Another term that is basically it is related to the maintainability. In this basically you have to maintain in a such a way that easier way without interrupting the supply or operation of the system. So, unavailability here due to the scheduled maintenance. A system may be unavailable because if it is going for the maintenance, and it is a maintenance is a two type. One is the emergency maintenance, another is the scheduled maintenance. Scheduled maintenance are decided in advance that you are going to maintain it in the future time, future date and time, etc., and based on that you can operate your system in such a way that should not be any chaos or any other problems. So, the design of HVDC light system here, what we do, it depends upon that how your HVDC light system is there, because if your HVDC light only 1-2 zones are connected with the one system, and once this line is open or it is gone for the maintenance, then sorry, what will happen? Then it is possible that we cannot feed the power from one zone to another zone. So, it depends upon, that is why it is run maintenance depends upon the design of HVDC light transmission system and also the organization of maintenance work. So, the unavailability basically decided based on this. So, modern design incorporates the very good cooling system. We require very reliable cooling system, and then also we go for the duplicated control system, and also we require the station service power, because sometimes the suppose emergency power is gone, some problems and the power is failed, then what will happen? So, we require some station service power that allows most of the maintenance work to be done without any interruption of the operation. Means the main intention that we should operate whole system, we maintain our system without interruption of the operation. That is the major goal of improving the reliability of the system. So, now let us see that we can go for, if you are using the VSC based HVDC system in the hybrid HVDC AC system transmission system, and that I am going to discuss. Cut. So, in this voltage source converter based HVDC system, if it is inbuilt in your AC/DC system, then it can solve a lot of problems. It can improve the performance, that is both static as well as your dynamic performance. So, here just I want to mention, if a AC transmission lines are parallel with the voltage source HVDC system, there will be more advantage, and that advantage that I can say, the rectifier uses the constant active and reactive power control, while the inverter uses your DC and AC power. That is the basic philosophy for your VSC based HVDC system. With the VSC HVDC, its ability of regulating the DC power can help to damp out the oscillation when the system has the fault. What I want to say, that if you are having, let us suppose you are having this is your HVDC light system, you are having this is a, just I am talking with a single line anyway. Now, here this is you are having a transformer and other things. Now, if you are having your transformer and you are having the two parallel lines, let us suppose, and then I am talking in this sense, and this is also you are having a transformers of the different rating. Now, what is happening? This is your HVDC light, this is I can say the VSC based HVDC system, and this is a parallel with the two lines. If there is any problem here, there is any fault in this of the line, then we can control that. As I said, this is a HVDC light system. You can control P and Q independently from the rectifier side. So, if there is any fault, what happens? Then system will keep on oscillating here. If it is not there, if there is any fault in any of the line, then the power will be oscillating and there will be swing. And that if you are using here, then you can modulate that power and that oscillations can be damped out, and that is the beauty of this HVDC system here. If a power demand of the receiver system increases, the system will lose its stability without this. If there is a fault and suppose this line is tripped and this is not there and the power demand this side there, then system also becomes unstable. But if you are using this, you can control the power, you can send power from this HVDC light, and this will improve. Basically, if you are having this, then it will be improving the system stability. That is why it is said that if the VSC HVDC system is put into the operation, the system can be kept stable, along with the performance can be improved or satisfied, whatever the performance you want, what is your goal of the performance, that can be met. HVDC light can improve the dynamic performance in the total, I can say, and keep the system stable for the power angle stability, just like the conventional HVDC system, and it also provides the damping for the system oscillations, as already explained. So, it can damp out the oscillations if in the AC system. By this we can damp out very easily. For the conventional HVDC system, the fault may cause the commutation failure. Here the major concern is this: if you are not using this, the option that you can have the conventional, let us suppose your HVDC system, if there is some fault in this side here, this voltage may go down, and this inverter, if it is a conventional base, it is not a VSC, then there may be possibility that there will be commutation failure, and also that will may cause their DC voltage going to down, and it may be 0, and that may delay their voltage recovery problem, and then system may be, even though it requires some more time to get stabilized. But if you are using the HVDC here, since there is no concern of your commutation failure, so we can recover the DC voltage rapidly. At the same time, by constant AC voltage control in the inverter, it can produce the reactive power and help the recovery of the AC voltage as well, and thereby we can very quickly restore the voltage this side, and we can your power system dynamics and whole power system operation in this AC/DC using the voltage source converter based HVDC is improving much better than your conventional HVDC system. Another concern here, this is we are having AC system, and then you are having a HVDC light system. Now, there is also possibility that you are having the HVDC system conventional, and then you are putting your HVDC light, that it also improves the performance of the system. For example, if you are having a HVDC system here, let us suppose I am having a HVDC system here, one parallel we are having the DC here, and we are having another HVDC here, let us suppose parallel to this, we are having the HVDC this side, this is your converter station, I can say, and here we are having, and then we are having the transformers, of course, connected with this. Now, this is your HVDC 1, I can say, this is a conventional HVDC system, here I can say HVDC 2, and this is, and the parallel is also operating, and this is connected with the 2 zones. In this case, what is happening, that if HVDC light put along with the conventional system, again the power system performance, the whole operation of the system is improved significantly. So, that is why it is said that a single phase to ground fault is set at the AC bus of HVDC 1 converter, and the faults inception here during this. If suppose you are putting some fault here at the point 4 is steadily operating, and the duration of this fault, let us suppose, sustained for 5 cycles, that is a 0.1 second, and then with this system HVDC light and without, we can see if this fault occurs and you are not having HVDC light system, then system becomes unstable. And if you are putting HVDC light system here, what happens, then system becomes stable, one conclusion here. Another, without HVDC light here, what will happen, there will be problem of the commutation failure of these two side here, this is the HVDC line we are talking. So, that also can be recovered by using the HVDC light. So, with the HVDC light, the converter 1 still has the commutation failure, but the DC voltage only decreases up to certain level, that is a 300 kilovolt, this is operating 500 plus minus volt. The HVDC 2 does not have any commutation failure, and the DC voltage only decreased to 0.8. If the fault is here, there is a possibility of the commutation failure here in this fault if you have occurs the AC side this, but this is not going to affect, and finally, with help of this, if it is not there, then no doubt there will be also commutation failure, but with help of this, this voltage will go down because this is maintaining the reactive power injection here, and then we can say that the system can be stabilized much more faster. So, the constant AC voltage control makes the inverter that produce the reactive power to sustain the AC voltage of inverter side due to this HVDC light system, and the AC voltage can be kept higher than 0.9 per unit, which prevents the commutation failure of the HVDC link 2. Also, this HVDC light has the capability of controlling active and reactive power respectively, and it can support the AC voltage and the DC voltage during the fault in the power system. So, in the multi-feed HVDC system, HVDC light can help the recovery of the HVDC system and prevent the commutation failure of these HVDC systems. So, this is again, if you are having the HVDC light in feed with the HVDC system, that again also improving the power system performance, and also it improves the performance of the DC links as well. So, in the remark of this HVDC light, I can tell you that the voltage source converter based HVDC transmission system is a few technology that has been specifically developed to match the requirement of new competitive electricity market. Now, the markets are appearing in which that every generators are competing with the other generators, and thereby this cost etc. is basically the price based, and the market is deciding the price of electricity. So, in that there is a lot of corridors basically getting congested, some of the lines even though going to be over congested. So, what happens with help of HVDC light or maybe your transmission system base, we can regulate, we can control the power in the very effective way, and then we can meet the requirements of this today's need, that is in new competitive electricity market environment. It also provides the accurate control of the transmission active and independent control of the active as well as the reactive power as well, and that is a big deal, because we can both active and reactive power control, which is not possible in the conventional HVDC system, where the real power you can control, but the reactive power cannot be controlled independently. So, a pair of lightweight DC cables can be laid direct between the ground and in the cost effective way, which is comparable to or less than the corresponding total life cost cycle of AC overhead lines. Now, no doubt the cable cost is larger compared to the AC overhead lines, but if you see the life and other things and other advantages of the cables, this cable may be, even though in the that is called life cycle LCC, is comparable to your transmission overhead transmission AC lines. It also provides the ability to connect the renewable energy sources to the AC grid. Now, this is one of the big challenge, because nowadays due to the smart you can say smart grid initiatives all over the world, now we are trying to integrate the smaller and smaller distributed energy resources into our conventional grids, and those smaller normally they are the renewable energy sources, maybe your wind, photovoltaic and other biogas and other tidal, whatever the renewable and small energy resources are there, along with the non-conventional as well, like the CHP and other micro turbines we are using. So, with the help of HVDC light etc., we can very effectively just integrate or connect these resources into the main grid without much disturbance, because these energy resources are distributed in nature. So, let us see, as I already discussed, the wind power generation, that is this HVDC is going to be very popular in the wind power generation, and let us go quickly, because this is not the wind power generation is a part of this, but since wind powers are there, so we are using HVDC for this. So, I am going to quickly review what is the wind power. So, wind power generation is environmentally friendly, as you know it very well, and the large unit capacity, because nowadays we are going for the larger and larger single unit. Earlier it was very small in the kilowatt, now we are having in the megawatt, now we have gone up to the 6 megawatt, and again some of the R&D and other activities are going to be installed more than even the 7.5 megawatt in the future, we will see it. So, we are going for the one unit is going to be larger, that is in the megawatt or so, and then if you are using a large number of wind units, then it is going to be a windmills, or you can say wind farms. So, that is a easy to develop large scale generation farms, and due to which it is considered as the most promising alternative energy resources compared to other one. So, nowadays only the two alternative energy sources are renewable energy sources, one is wind, another is the solar, are very promising nowadays, and wind is one of them, and that is more popular. So, already in all over the world, the integration of the wind power energy into the conventional grids is going to be more challenging, and people are putting more and more into the system. Sometimes the geographical and the electrical restrictions exist to offset the further increase of the wind power introduction capacity in the some of the area of the world. That is true. Why this we are talking the geographically? Because sometimes if you are having a location is some awkward, that it is not possible to build a transmission line, or maybe it is not possible to have the cable or so much, that is geographically, and also you are having the line, but it is overloaded, and other thing your network is not capable to sustain. So, that is why it is a geographical as well as the electrical restrictions may do exist, and thereby that may offset the increase of the penetration level of the wind power resources. So, you can see we will see some other wind power generation features, but here you can see wind power generation, which is you can say it is a wind farm. It is not only one unit, it is the one unit cannot be a 200 MVA, but it is we are having so many units together, then it is called wind farm, and that's capacity efficiency in this here it is shown this 200 MVA or 200 megawatt. So, it is connected at the bus 1, then we are having the step up transformer, and then we are going for the 150, and you can say this is the DC cable, because it is possible that we can go for the AC overhead lines as well, but it is depends whether it is your offshore or your onshore. In offshore we have to go for these cables, because the construction of your towers and the overhead lines are very expensive. So, it is your transmission line, and the distance it can be a DC cable, very well we can use here HVDC light, and then again step down or step up, and then you can connect to this your other system, maybe your lower voltage, medium voltage, or maybe EHV or USB high voltage, depending upon the power injection into the system that is allowed. And you know this interconnection, the PCC we call the point of common coupling, it depends upon the grid code of the respective country, and that is decided at which level how much power you can inject. So, beyond the sum of the transmission distances, I say if your distance is very far, the 3-phase current network using submarine cables were no longer technically feasible, and the 3-phase basically here talking the 3-phase means AC, it is no longer technically feasible, nor can the stability of the network concern be assured in all control states of traditional means by rating involved. So, instead of traditional thyristors, we can use the IGBTs component are now being used, and the microprocessor based and the computerized control systems have been replaced with their the old air analog controls, and thereby we are having very fast and very efficient controllers, and we can transmit power over the DC cables. So, the development basically process has given the new generation of the HVDC transmission equipment, and it is branded at the voltage source based HVDC, or called HVDC light or HVDC plus. So, the voltage source converter base has already we saw the lot of advantage compared to the CSC based HVDC transmitter, and CSC base is nothing but your conventional HVDC transmission system. So, the VSC based HVDC system can be supplied up to a unit of output vector only 500 megawatt, and this power can be transported over a longer distance with the low loss using just one pole of the DC cable, one wire that can be returned, ground can be returned, path can be used. So, the property of wind farm, here I have written this offshore wind farm power generation. You know, offshore means it is some of the countries are having the sea, and that sea is very shallow. So, they can put their wind turbines inside the sea, and it can go up to the 70 kilometers or 80 kilometers. So, that we need you can track the power, and this has a main advantage, you have to receive and collect the power, and you have to send the land, and thereby that can be utilized for the your load. So, compared with the others, here it is said in this slide that compared with the land wind farm, that is a onshore wind farm, offshore wind farms has many advantages, such as is easy to find the suitable sites, because the land maybe you are having trees, you are having so many other obstacles, your land is not uniform, sometimes vertically, and wind also is another concern. No, you can say here written the excellent wind profile. In the wind, you know, you are having the wind almost a longer duration compared to your land side, and also you are having very constant speed that is required for the production of the power. So, first one that we can get the site very easily, because the land the sea we can use the no doubt the cost will be slightly higher, but again the technology are improving for the offshore, and the cost is not a big concern now. So, excellent wind power profile in the offshore, and also the satisfactory economic effects can be expected from the offshore wind power generation. The scale and the capacity of the wind farms can be determined with the large flexibility and easy to be expanded. Suppose you are having the certain units right now due to the cost and other criteria, later on you can add, and finally you can transport it. So, it is very easy to expand as well whenever it is necessary in the future. Offshore wind speed accelerate, and since it is not hindered against the obstacle of the sea, and that is why the speed accelerates, and very easily we can just trap the power. The wind speed basically here the offshore wind speed is obviously stronger than the land speed, it is a high speed, and in this case especially the difference of 2.3 meter per second on average can be observed, means you are having always 2.3, then your land you can find it is average, and then your output can be larger compared to that your land wind power stations. Since the wind energy is the third power of wind speed, I want to say that wind power or wind energy is proportional to the cube of the wind speed. The energy obtained from the offshore wind is a possibility 2.4 times more than your wind speed, land wind. So, whatever the power, if the speed is more, so it is a cube of this. So, you are going to get more and more power, but no doubt you should not be confused that if your speed is very high, then you can get more and more power. So, always that we operate our wind turbines in the two speed. One is called cut in speed. If speed is less than that, the output will be 0. If speed is very high, then it is a cut off speed, and then you cannot produce and you have to shut off your wind turbine. So, in between, but no doubt we can have the large energy power production, and we will see some slides and some figures in our next presentation. So, standard deviation of the land speed appears dramatically fluctuating in the high speed zone, but with the offshore the wind speed seems considerably flat with the less fluctuation, and offshore wind can give the larger as well as the most stable wind power compared to the land, which we can see in our next slides. Basically, I will show you. You can see this is a wind power generator. In the previous slides I saw one figure, but here only I said this blade and the wind turbine, but you can see in the wind turbine you have so many things. You have a pitch angle control, we are having the basically now we require the maximum power tracking algorithms, and also we are having the excitation control of the synchronous generator. Then here you are having so many things, again different type of wind power generators are available. You can have the induction generator, you can have the doubly fed induction generator, you can have even the synchronous generator. So, and these are using basically the power electronics based interface, and then finally it is coming into the picture, and you can say this is your DC transmission circuit, and finally it is integrating with the grid, and this is the system. So, it is a simplified model for the offshore wind power generation, which is having the cable and along with your wind power system, which is collecting. So, offshore wind power generation system has been constructed by taking consideration of the following aspects. So, various aspects are considered when you are going for the offshore wind farms. So, selection is the basically based the selection of the best location suitable for building the offshore wind farm is to be, first you have to select the good location, you have to see the wind profile throughout the year, so that you can see what is the cost, how much your recovery is there, and that must be very carefully designed. So, it may have the dozen or even hundreds of wind turbine generators to obtain the larger capacity. As I said, we are having still not going, we can have a 100 megawatt of a single unit. We are having a limited less than the tens and of the capacity, and then we have to go for the so many units to be connected in series and the parallel, so that we can have more and more power output. So, generator may be of type, as I said, the induction generator type. We can have the doubly fed induction generator, or we can have the synchronous generator. Normally, the synchronous generator we use the permanent magnet synchronous generator, so we call the PMSG. And at least some of them should have the DFIG and SG, because there is some problem in the induction generator, you know all this, it is not self excited. However, the DFIG and SG are self excited, and then we can do it. So, that is why it is said that you should have some of the units of DFIG or SG along with the IG if you are using. The generated wind power may be transmitted to the power system via the land, on the land via an AC or DC transmission circuit. So, if it is offshore, then you should have the AC cable, in offshore AC cables or the DC cable, and the DC cables have a much advantages than to your AC cables. So, the DC transmission circuit consists of converter stations at the sending offshore sides, including a conversion transformer and the bridge circuit. We also require the switching devices for both the converter and inverters, and normally we use, if you are using IGBTs, then it is HVDC light, and as modulated by the pulse width control normally we use. The basic design of the transmission circuit and its control is always one of the big concern, and it should be designed in the very proper way. You can see here in this you can outline of a typical offshore wind farm. You can see here we are having all this 1, 2 to 10 units in one parallel, then here again 1 to 10, and then 3. So, you can say that here the 10 units, 10 units and 10 units, the 3 rows are there. So, totally you can say is a 30 units are there, and if you are having one unit after 10 megawatt, then you are having the 300 megawatt. Although this we do not have right now 100 megawatt of one unit capacity, but you can say here again you can add 1 or 2, then it is going to be 2. Suppose you are having 2, then it is going to be 10 megawatts. So, it is connected again your DC cable, and finally, it is connecting to your grid, and that is the infinite here is so that you are having infinite bus. Basically, it is showing your complete power system having huge inertia. In the control side, you can see the converter, the control blocks. What we do in the converter side, you can see the DC voltage and the DC voltage reference is compared, then we are having some phase angle of AC system, both are coming, and these signals are given to the pulse width modulated control, because we are generating a sine wave. Similarly, if we are controlling the inverter, here the voltage AC voltage is checked, then we are also controlling the active and reactive power reference value here, and the phase angle and the inverter output both are coming, and then it is based on that we are generating the phase angle. This is some schematic diagrams that is normally used. Some people go for the different type of control structure, it depends upon the various type of control philosophy. Here, as I was telling that, you can see the offshore wind power output is considerably higher than that of land wind speed, with the relatively less blast and the sharp fluctuation. You can say this red one here, this is having the land wind turbine speed on the land. You can say it is always less than your offshore wind, and you are having more here. You can see, and also we will see here in this next slide, you can see here is a dark here black, dark black, and is a light black here. The dark black is from your offshore power output, and you can see here is also, you can see up to here that is a 24 here, 24 to 52, this output is 0, because this speed is less than its speed of that is a cut in speed. So, your turbine should be off and there will be no power generated. However, you can see your offshore still, even though that low speed at the land, you are having some speed in the wind and you can generate some power. And also you can see the fluctuation here is a huge fluctuation here compared to this land side, and that is why we can say offshore wind power generation has a much higher stability and higher rate of operation, and that may lead to the higher performance of efficiency as well as the better profitability, because you can generate larger power, you can get maximum profit, whatever the cost you can recover in the quick time, and that is why we can say there is the profitability is there. So, here I want to conclude that the wind power is one aspect that we can connect the wind power with the help of your HVDC transmission system, especially if you are having the offshore. If you are having the onshore, then it is possible that you can go for your AC transmission system, that is a overhead conductor, that is possible, and then you can construct and then you can connect with the main grid. But again, if you are having offshore, then it is not possible, then you have to collect the power and then you have to use the cable, and you know the AC cables are having a lot of problem in terms of reactive power charging, and the DC cables are one of the option that you can feed more power, and also the cost can be minimized. So, among the various type of renewable energy sources, the offshore wind power generation has the advantage of the large capacity, excellent wind profile, and the high operational performance, etc. is possible. In some of the country, it is not possible that we can go for the offshore. If your sea is not shallow, then suppose it is very deep. So, you cannot your cost of the construction of a wind turbine, that is a platform, it is very expensive, and this is not feasible. But especially in the Europe, the sea is very shallow, and they are using lot of offshore wind power plants are coming, farms are coming, and thereby they are just injecting lot of wind power into their grids, and they are basically backing down the thermal power and using the renewable energy sources. So, based on the prediction of the offshore wind data using the measure the land data, a basic structure of this generation system with the self commuted HVDC transmission system is suitable. Self commuted here, it means your HVDC voltage source converter based technology, means that is HVDC light. Your line commuted means your conventional HVDC system. So, offshore wind is stronger and stable than the land speed, it is very well known, and this always, and also the continuity and availability is much more in the offshore. Always you can experience this. If you are going in the near to the sea, you will find there is always breeze, and then always the wind is flowing, and inside sea also up to 70 kilometer you will find the constant almost speed, although fluctuation is there, but it is very less compared to land side. And also on the land side, the speed maybe the speed is there, but it is not a curly, maybe some gust and something other things are there, which we cannot use our wind turbines. So, the offshore is one of the need of the hour, and it is going to be more and more added, especially if it is feasible. The power generation by offshore wind is considerably higher, as I said, because you are having the higher speed, and then you can basically generate higher as well, and that is good enough. And the relatively fewer blast means the change, sudden off and on, and the sharp fluctuations are not there in the offshore. However, you will find in the land or you can say onshore wind turbine system. Self commuted HVDC transmission system is able to enhance the system's stability by maintaining the fluctuation of both the DC transmission circuits as well as you are having the AC transmission system with the properly designed control schemes. Means if you are having the designed control systems, better performance can be achieved by this voltage source converter based HVDC system. And even in the case of the serious contingencies, contingencies means the outages, if there is some outage of any of the elements, then the whole system has ability to keep continuous operation by this system if you are having HVDC system. So, thereby that you can improve the system operation as well, and that is the one of the option, and that is a very much desirable. So, with this I can conclude this module 7 and that's lecture number 3, and with this whole this HVDC system, this is the end of this lecture, end of this class, end of this course, that is the HVDC transmission system. Thank you.